Good evening, my dear warriors. I hope I'm audible and visible. Welcome to the part number 2 of magnetism and magnetic effects of current as well as the sources. This is your Captain Shreyas, your physics master teacher on the Vedantu NEET English channel. Good evening, Krishna, Madhumati. Wow, the chat box is warmed up already. Thank you so much. Hi, Sukanya. Hi, Jasmine. Hi, Marday. Good evening, Shivali. Good evening, all the warrior Pandus. Thank you so much for lighting up the chat box. And well, here we are as we complete almost the chapter number 4. Just few more chapters, guys, and you will be done with part 1 and slowly we'll begin with part 2. And for all of this, I need your support so that we complete the entire NCERT line by line, decoded, first time on YouTube in English. Nobody has done it, guys. And that's the reason why I'm doing it for you. It is for you, for your benefit, because remember, I know that many students suffer a lot because they have not gone through NCERT or not understood NCERT. You go through the NEET aspect, but sometimes miss out on all the crucial statements. That's the reason why we are doing it. So quickly like as well as subscribe. So in the last lecture, in the part 1, we have done a lot of things. Let me just quickly go through all these things right away right now. So we started with Orsted's experiment on how current carrying wires can produce magnetic field and how electric field is slightly different from the magnetic field. And in the last lecture, we have seen how magnetic field affects charges on current, charges moving which are charges which are in motion or currents. And we also saw how current produces magnetic field around it using Biot-Savart's law. That is what we have done. We have learnt about magnetic field. We have learnt about the Lorentz force, QV cross B and QE together. We have done quite a few examples. Force on a wire which carries current, which is IL cross B. That is what we have done. And also, if you have a curved wire, then you can just join the endpoints to find the effective force. And also the force on a complete loop is always going to be 0. That is what we have seen. Also some special cases of a charge moving in a circular path. What is the radius? What's the time period? And a charge which is thrown at an angle, then it ends up going in a helical path. That also we have seen in the previous lecture. We have also seen Biot-Savart's law. All of this, okay, Biot-Savart's law, which is nothing but the magnetic field generated by a current carrying wire is given by IdL cross R divided by R cube, mu naught by 4 pi, where mu naught is permeability, something like permittivity. All these things we have done. Magnetic field due to a coil on the axis also we have done. Okay, all these problems we did. All right, like I said, that we'll be doing now Ampere's law, which was in part 2, right? That is today's lecture. So let's begin with the lecture, right? Okay, let's start. Welcome aboard everyone. Okay, so now see, in the chapter of electrostatics, what we had was Coulomb's law, and then we also had Gauss' law. If you remember, Coulomb's law was helpful when you had point charges, etc. Gauss' law was helpful when there was symmetry to find out the electric field. You have seen applications like a long wire which is charged, what's the field around it, or a shell or a sphere, how to use Gauss' law for symmetrical bodies to find the field. Coulomb's law is used for point charges or rings and stuff like that, where it becomes easier to find the field. From this you can get this, from this you can get this. These both are dependent on each other. Same thing happens even in magnetism. We have just studied nothing but our Biot-Savart's law. This law is, like I showed you last time also, is helpful for elemental currents. If you remember correctly, it was good for elemental currents and how to find the field due to that. You take an element of the current, what's the field which is very small, dB, due to that, and you can add them up to find out the net magnetic field due to all the current carrying elements. So is there a law which is like Gauss law but in magnetism? Something like Gauss law but in magnetism, which helps us for symmetrical geometries? The answer is yes. That is called as your Ampere's law. From Ampere's law, you can get Biot-Savart's law. It is dependent, and so is this. They both are dependent on each other. Just like this is used for symmetrical bodies by choosing a closed surface, here it is used for symmetrical bodies in general, but instead of a closed surface, you choose a closed loop. So there is always some small difference, like, it's same but different. So just like in electrostatics you had permittivity, in magnetism you have permeability. If permittivity was 1 by 4 pi epsilon, epsilon was their denominator. In magnetism, it was permeability which was there in the numerator. It became mu naught divided by 4 pi. So similarly, if there is Gauss law kind of a thing in electrostatics, which is for a closed surface, you had enclosed charges. This is for a closed path, and you will have, instead of closed or enclosed charges, you will have enclosed current. So that is what Ampere's law is all about. So there is an alternative in which Biot-Savart's law may be expressed, and Ampere's circular law considers an open surface boundary. When the surface has a current passing through it, consider the boundary to be made of number of small elements. So this is basically an alternative appealing way. Why they said appealing is because it is easier for symmetrical geometries instead of Biot-Savart's. Therefore, you use Ampere's law. Okay, and they have explained what the elements etc. are, and finally they have given the Ampere's law right over here, which is integration of B dot dl is mu naught I, and okay, so that's what they have given, where I is the total current through the surface. All right, this is the loop integral. Loop integral is B dot dl, and the direction of the thumb gives the sense in which the current I is regarded as positive. For simplified version proves sufficient. Okay, and all these things they have mentioned over here when there is a system. Okay, so let's talk about what is Ampere's loop law. Say for example, you have a wire which carries some current, let's say I1. There is another wire which, let's say, carries current I2. Another wire over here carries current I3. Another wire over here carries current I4. Another wire which is over here, let's say, carries current I5. All these are random wires randomly placed here and there, carrying currents of different amounts in random directions. Now, around it there will be a total magnetic field. Each wire will produce its own magnetic field. So there will be magnetic field around those wires. So let's say you are somewhere, maybe over here, and you note down what is the magnetic field, and what you do, you keep on traveling, maybe around these wires, and you come back to the same point. As you travel and you come back to the same point, this entire closed path, this particular closed path, any such closed path is also called as an Amperian loop. It is called as an Amperian loop. So if a dog runs and comes back to his owner, so the path which the dog takes is called as an Amperian loop. You go to the school and come back to your house only, that path which you have taken, complete path, is again an Amperian loop because you have come back to the same point. Okay, fair enough. Now, once this is done, what you do next, at every single point, try to figure out what was the magnetic field and take the dot product of that magnetic field with the displacement that you undergo. Let's say that displacement is dl. So You are taking the dot product of the displacement with the magnetic field. You go to the next point, there will be a new magnetic field, and take the dot product with the displacement there. So at every single point, there will be a new magnetic field, there will be a new displacement, and you keep doing the same thing, throughout that particular loop for all the points, B dot dl, B dot dl, B dot dl, B dot dl, and you add them up, because there will be many such points. In fact, a line is made of infinite points. So you're adding up infinite numbers, but each number is a very small value. So such a thing is nothing but called as an integration. So therefore, summation same as integration. Summation and integration means the same thing. But since you came back to the same point, that is why I will use this symbol. So this is a closed integral, but I am integrating not with respect to area, I am integrating it with respect to the length or the path, or a line or a curve. So that is why this is called as a closed line integral. But this is of whom am I integrating with the rest? Of the magnetic field. Why closed? Because I came back to the same point. Integration because I am adding up. Line because there is a dl. Whom am I integrating? Magnetic field. Is this clear, everyone, till this point? Okay. Now when you do this, what you get on the right hand side is very important. What you get on the right hand side, you basically get mu naught, which is permeability, into a number. Now what is that number? Let's understand it. This was the closed path. So imagine a film, soap film, which is enclosed by that line integral. Imagine a soap film. Imagine you take that path, you dip it in a soapy liquid and take it out. A soapy film will be formed, thin layer will be formed, and that is how you can visualize which currents are cutting through, are piercing through that particular soapy film, or that Amperian loop. So these currents are basically the currents passing through this imaginary path. These currents are also called as enclosed currents. Why is I phi not an enclosed current? Because it never pierces this particular thin film, or this passes through inside that particular path. Even I4 is an outside current, it is not piercing through it. I1, I2, I3 are piercing or through that film, or they are passing through that particular Amperian path. That is why they are called enclosed currents. So I will put over here currents enclosed. This is basically called as your Ampere's loop law. Is everybody clear till this point? Give me a thumbs up if you understood it till here. Okay. Now, please remember over here, this magnetic field is due to, this particular magnetic field is due to both inside as well as outside currents. Not just because of outside or not just because of inside, but the value of this integration is only because of the enclosed currents. Now you might be wondering, what is the value of this enclosed current in this particular case? What is the value of this enclosed current in this particular case? A lot of you might think, sir, I1 is there, sir, even I2 is there, sir, even I3 is there. So I1 plus I2 plus I3. That is not correct actually, because even these currents have a sign. Now you might be wondering, sir, what is the sign of this? How is current given a sign? Very straightforward. Take your right hand, take the fingers of your right hand and go in the same way the loop has been covered. I am going across the loop like this. So curl your fingers of your right hand, curl your fingers of your right hand exactly in the same direction. Okay, in the sense in which you are covering the closed path. Then what happens is the thumb exactly points in the positive direction of the current. So if you notice the thumb is going up, so I1 and I3 are positive. So I1 and I3 are basically positive currents. I1 and I3 are positive currents, but I2 is going down, so that will be considered as a negative current. So you use your right hand thumb rule to figure out which current is positive direction and which current is negative direction. I hope this is absolutely clear. Yep, very, very important. So that is exactly what they have mentioned right over here. They are finding the magnetic fields at all the points. They are multiplying it with the taking the dot product with the length, and then they are adding it all together, and then they are adding many elements. So it is integration, but since they are coming back to the same point, it is called line integral. It is called as line integral of the magnetic field. They have also mentioned the direction of the thumb gives the direction of the positive current. That is what they have mentioned. Okay. Now they have also given a simplified version of the magnetic the Ampere's loop law, but that is not needed actually most of the times. All right. They are told B into L is equal to mu naught into current. Don't worry about it so much. That's simplified version. So I'll just explain to you what that simplified version is in a bit. Hold on. And then they derive the magnetic field due to a long wire which is carrying current. Okay. So they have derived the magnetic field due to a long wire which is carrying current. So what do they mean by this? See, if you take a long wire like this, if you take a long wire which is basically carrying current, and I want to find out the magnetic field at some distance from it. I want to find the magnetic field at some distance r from it. So what I do is I can use Biot-Savart's law. Second option is I can use Ampere's law. Ampere's law will be beneficial because it will simplify your problem. How? Let's observe. Due to this current carrying wire, the magnetic field lines will be circular in nature. Everybody agrees with this statement. The magnetic field lines will be definitely circular in nature around this particular thing. So there will be some magnetic field lines like this maybe. There will be some more magnetic field lines like this maybe. Then a magnetic field line exactly passing through that particular point, maybe somewhere over here. So this is how the magnetic field lines will look like around that wire which is basically carrying current. Around this particular wire which is basically carrying current. Okay. Now, in order to find how much this field is at any distance r, obviously as r increases, the field strength will reduce. I will choose an Amperian path now. I will choose an Amperian path or Amperian loop. Amperian path means I should come back to the same point. So I will start from here. I will go exactly around this particular wire along the magnetic field line. You will see why that is beneficial for me. I will complete my path by coming back to the same point. So that is my Amperian path. So what happens is, because of that, at every single point, whatever my displacement is exactly in the direction of the magnetic field. Displacement is in the direction of the magnetic field. So because of that, what happens is, if anybody does magnetic field dot the dl vector, the answer to that will be A dot B is A into B into cos theta, in this case cos 0. Why? They are parallel to each other, and cos 0 is basically 1. So hence I'll be just getting B dl. B is magnetic field and DL is basically that small length. Everybody clear till this point? Everybody clear till this point? Because cos 0 will be just 1. Okay. Next important thing is, if I apply Ampere's loop law, which is nothing but integration of B dot dl is equal to mu naught into whatever is the current which is enclosed. This B dot dl will be just B dl. That means that B will be constant, it will come outside. Inside the integration, I will be just left with dl. I'll be just left with dl. What happens in the next step? Think about it. If I add all the small lengths and come back to the same point, I'll get the circumference of this Amperian path. I'm just adding all the lengths and I'm coming back to the same point. It is circumference, and circumference of a circle is nothing but 2 pi r. So basically the LHS becomes B into the length of the path. This will just become the length of that particular path. That is what the LHS becomes. That's exactly what they have told over here. BL, that is what the left hand side becomes in a simplified version. Are you able to see that? B into L. So for a simplified version, the left hand side becomes equal to magnetic field into L, where L is the length of the path. L is the length of the path. That is exactly what has happened on the left hand side of the Ampere's loop law. Cool? Okay. So that length of the path in this case is 2 pi r. Alright. The magnetic field is as it is. If you talk about what is happening on the right hand side guys, right hand side, what is the current which is passing through that Amperian path? It is only I. So only I will come over here. So hence, rearranging, I will get magnetic field as mu naught current, this divided by 2 pi and r. That's the answer. That's the magnetic field at some distance of r. Okay, mu naught I by 2 pi r. If you remember, for a circular loop, it was mu naught I by 2r. Let's go back and see that. Formulas look very similar, same but different. Just for a circular loop at the center, it was mu naught I by 2r. There is no pi here. Be careful about it. There is no pi here due to a circular loop. Remember, circular loop at the center. The magnetic field was mu naught I by 2r. Now this is magnetic field due to a long wire, and that is mu naught I by 2 pi r. Is this absolutely clear? A small difference over there. Correct. So this is a beautiful application of how, without actually integrating, you have found the answer in a much easier manner using Ampere's loop law. Okay. So guys, if you are loving all these derivations, I hope you are liking the session. If you have not liked the button, please do that. That is your Guru Dakshina, or else whatever you learn will never enter your head. You should always give Guru Dakshina. No matter YouTube, physical class, online class, this, that, should always be grateful. Okay. This quality content which I am getting for all of you, so which is made easy, decoded, NCERT line by line by your Cap 2. Okay. Now they are telling that there are some interesting things about the infinite wire which we just did. This is an infinite wire. It implies the field at every point on the circle radius r is the same magnitude. In other words, the magnetic field possesses what is called cylindrical symmetry, which is normally dependent on 3 coordinates, 1 r. Whenever the direction is symmetry, solution simplify. So they are saying about cylindrical symmetry, which makes sense. Just look at it. The magnetic field lines are concentric circles. Below this also there will be concentric circles. Below this also there will be concentric circles. You can see they form cylinders. So that is why they are saying cylindrical symmetry. Anywhere you go at the same distance, here or here or here, as long as these distances are same, the field is the same, and that is the reason why we were able to so easily do this problem. They are telling why the problem was easy. So the solutions were simplified because of this symmetry. The field at any point on the circle is tangent, thus the lines of constant magnitude of the field form concentric circles. The constant magnetic field lines form concentric circles. The iron filings are also in the concentric circles. These lines are called as magnetic field lines from the closed loops. This is unlike electrostatic field where they originate from positive and end at a negative charge. The expression for magnetic field which was provided provides a theoretical justification of Ørsted's experiment. Now, if you notice in this particular paragraph, they are telling how magnetic field is different from electric field, and this is exactly what Ørsted had told. So if you notice, these magnetic field lines are circular. So if somebody sprinkles iron filings which are themselves magnetic in nature, they are also going to be in concentric circles because they will align themselves, because they will be affected by the magnetic field. So they will also become circular. These iron filings will feel like as if they are, around that current carrying wire in concentric circles, which is justifying Ørsted's experiment. If you had forgotten, we have done this at the beginning of the previous lecture. Current carrying wire deflects any magnetic material, and if you sprinkle some iron filings, this is how the iron filings look like. It just proves exactly the same point, that magnetic field lines are circular along the tangent. They go around in loops rather than starting at some point and ending at some point. That is also something which I had mentioned in the previous lecture. They don't originate or terminate. They will be always in the form of closed loops. Everybody with me on this? Shall we go ahead? That is the second pointer. So it's like a summary of whatever we have done till now. Another point to note is that even though the wire is infinite, the field due to it is at a non-zero distance is not infinite. It tends to blow up only when we come very close to the wire. The field is directly proportional to the current, and the field is directly proportional to the current and inversely proportional to the distance from the current source. Now, this is also very interesting that somebody might say, sir, this wire, sir, was infinitely long. So the wire is infinitely long. So the current should also produce infinite magnetic field. That's not true. See, in this region, these currents will affect and create magnetic field. But these currents here, they are very far away. They will have negligible effects. So even if the current extends till infinity, this will have hardly any effect over here. So don't worry and think that, sir, if it is infinitely long, it will produce infinite field. No, the far away elements have negligible contribution in that. Okay, the closer elements have significant contribution. It's like saying people around you are paying you 100 rupees, 200 rupees, 500 rupees, 700 rupees, and the faraway people are not even paying you 1 rupee. They are paying you 0.1 or 0.01 rupees or 0.005 rupees. So you will ignore them because it's not going to add to your richness or your wealth. Making sense? So that's why we do not count it. That is exactly what they have told. And yes, magnetic field is proportional to the current and inversely proportional to the R. So if you go far away, the field will reduce. It will only become infinite in one case, when you become R as 0 or you are very close to the wire. That means you are somewhere here. That means when you are somewhere here, then the field will tend towards infinity. In fact, if you draw the graph of the magnetic field versus the distance, that graph will look something like this. The farther you go, field will reduce. The closer you come, the field will become extremely large. That is what the third point says. There exists simple rule to determine the direction of the field. This rule is called right hand rule. Very simple again, right hand rule. They say that grasp the wire in the right hand with your extended thumb pointing in the direction of the current. Your fingers will curl around the direction of the magnetic field. What it means is, say for example, I will hold a wire I will hold a wire like this, just trying to make it look as real as possible. This is a wire which carries current such that our thumb of the right hand is pointing exactly how the current is moving. If the current is going like this, our thumb also points in the same direction. If the current was going down, I will hold the thumb like this, the fingers will go the other way around. So whatever direction my fingers curve, exactly that's the direction of the magnetic field. If the current was going down, then the fingers will curve like this, then the magnetic field will be this way. Got it, my dear warriors? That's the simple way of determining the direction of the magnetic field, clockwise or anti-clockwise. Easily we can get it. Clear, everyone? Very good, Bhuna, Krishna, Madhumati, Sivali. Everyone with me on this? Right. Great. Now, they have told that Ampere's law is not new. They both are related to each other. Okay, I think this particular thing is related to this particular statement which I mentioned here. Coulomb's law depends on Gauss law. Gauss law depends on this. If this is not valid, even this is not valid. Same way, if this is not true, this won't be true. If this is true, this will be true. They both are basically different ways of approaching a problem. This is used for different geometries. This is used for symmetrical geometries, just like over here. And then they have given an application of Ampere's loop law right over here. It shows a long wire which is carrying current. It has a circular cross section and it is distributed uniformly. Calculate the magnetic field below A and above A, where A being the radius. Let's understand what this problem exactly means, and then they have solved it. This by far is one of the most important problem of NEET, because they have asked this question almost every year in the last couple of years. This particular question and the graph, the formula, the problems, almost every last couple of years they have asked it. See guys, imagine there is a wire like this, okay, and this particular wire has a radius A, has a particular radius A. So if you look at it in 3 dimension, it will probably look like this. Okay, it might be carrying some current like this. This is that particular radius. It's a long cylindrical wire. Usually our wires are thin, but that thin wire will also, even this pen also has some thickness. It also has some cross section. Now, if you hold the thumb in the direction of the current, you can see the fingers are curling like this. Hold the thumb in the direction of the current. You will see the fingers are curling like this. That means around this, there will be magnetic field lines in this particular manner. So definitely there will be magnetic field lines around it like this. Even here. Not just that, even inside of this, there will be magnetic field lines. Even inside of this, there will be magnetic field lines. Yep. So there is magnetic field around the wire, not just outside but inside. The outside part, we have already done it. Yep. The outside part, we just figured it out. This is outside the wire. What is the magnetic field? But what is it inside? What is it inside? That is what you might be wondering. That is what you might be wondering. So, exactly that is our question. R more than A is already taken care of. This is when you are outside. Okay, check the previous slide. Check the previous slide. Definitely this was done. This part was done right over here. Right over here. This is the formula. Mu naught I by 2 pi r, where r is the distance from the central point or the central axis. Now the question is, what will it be inside? That is what our primary concern is. So now for finding that out, okay, I don't need this anymore. I will just draw a few loops here and there, magnetic field lines. This is how the magnetic field lines will be, circular in nature. Let's assume that the current is going inside. If the current is going inside, it will be going in everywhere. It will be going in here, it will be going in here. So basically the current is going inside the plane, That is the reason why then the magnetic field lines will be clockwise. You can see that the magnetic field lines will be clockwise in nature like this, and I want to find it at any distance r. So let's just say this is that r distance at which I want to find the magnetic field. This is basically your r. Okay. Now at that particular point, obviously the magnetic field will be tangential to the circle. So the magnetic field will be always like this, correct? So that is your magnetic field vector. Everywhere it will be tangential along the circle. So I will choose my Amperian loop smartly by moving around that circle, because I know if I move around that circle, exactly the same thing will repeat over here. B into length of the path. If I make sure B is along the length that I travel, cos 0 will be 1, and the left hand side will be exactly this, isn't it? The left hand side will be exactly this. So I will choose a smart Amperian loop, and that smart Amperian loop will be basically going around exactly the same magnetic field line. So this is my Amperian loop. I will go exactly like this, and that will be my DL vector. DL and B are parallel. That is my Amperian loop. So the left hand side of Ampere's law will just become magnetic field multiplied by the length of the path. The length of this path, because the radius will be r, distance was r, so it will be nothing but 2 pi r. So 2 pi r into B will be the left hand side of the Ampere's loop law. Everybody fine till this point? Clear? What's the left hand side? What about the right hand side? Of the same thing? So let's try to do that. So what about the right hand side of Ampere's law? Now that is going to be slightly tricky. You have to just figure out what is the enclosed current. Realize one thing, only this much current is enclosed. This current should not be even counted. I hope you see that. Only the current here should be counted, the outside current should not be counted. So how do I do that? How do I find the current which is passing through it? Yeah? Capto, please explain the tangent part once. Okay. See, like this, the magnetic field lines inside, where is it? So this was our wire, right? The magnetic field lines will be like this, concentric circles. The magnetic field lines will be concentric circles. So if I draw tangent to any field line, what does it give me? The direction of the magnetic field. If I again draw tangent here, it gives me the direction of the magnetic field. If I draw tangent here, it gives me the direction of the magnetic field. If I choose my Amperian loop also exactly along that magnetic field line, everywhere my magnetic field is parallel to the Amperian path. Everywhere the magnetic field is parallel to the Amperian path. So the angle between them is 0. Because the angle between them is 0, that's why it will become a very simple term, B into the length of the paths. Is that okay? So I've just gone around it in a circular path along the tangent. The reason why I went along the tangent is because field, dl, everything will be parallel at every point. So the cos 0 will become 1. Cos 0 will become 1. What am I talking about? Cos 0 becoming 1? This one. The angle between them being 0, cos 0 will become 1. So it becomes a simplified equation. So this is your simplified equation. This is your simplified equation. Cool till this point? Krishna, is it clear? Okay. Now coming back to the right hand side, what is the enclosed current? It is clearly mentioned that the current is distributed equally. So if the current distribution is equal, current distribution is uniform, it means that the current which is there per unit area should be basically the same everywhere. If you take any one unit area, whatever current passes here versus passes here versus passes here should be the same. So current per unit area will be the same. So if you see the total current of I passes through this entire area, which is going to be pi into basically a square. But the enclosed current, I enclosed, is only through this much. So that will be having an area of pi r square. So these both should be equal. Current per unit area should be the same. Clear? Now, therefore, pi will cancel. What will I get as the enclosed current as? I will get it as I into small r square by a square. I into small r square divided by a square. So the right hand side will just become mu naught into I enclosed. So that I enclosed itself will just become I into r square divided by a square. So that's it. That will give me the final formula then. So combining LHS equal to RHS now. So if I do LHS equals to RHS, okay, where did it go? Yeah, LHS was B into 2 pi r. LHS was nothing but the magnetic field multiplied by your 2 pi r. RHS is nothing but your mu naught into enclosed current, which is I r square by a square. So therefore, I will get the magnetic field as mu naught current. R got cancelled, 1 r will remain, 2 pi will go below, a square will remain below, and then you just have r over here. So this is the magnetic field. This is the magnetic field formula that we are getting. Inside this is mu naught I r by 2 pi a square, slightly different from this mu naught I by 2 pi r. Here instead of r below, it is gone on the top, and then there is a square over here. So from this, we figure out that if you are inside, the formula is mu naught I by 2 pi a square into r. If you are outside, the formula is mu naught I divided by 2 pi r. Here it is proportional to r. Here it is inversely proportional to r. So basically, if I show it graphically, on the horizontal line is the distance, on the vertical line is the magnetic field. As long as you are inside, As long as you are inside, the magnetic field will be proportional to r, that means a straight line. But after that it goes down like this, and this point is exactly A. So this is the maximum field that you get, and this is at the surface. At the surface you get it maximum, and after that it is inversely proportional to that. Is this absolutely clear, everyone? Okay. So very, very interesting problem of going inside. There are magnetic field lines inside also, outside also. So for finding it inside, we take a small loop inside the cross section of that wire, apply Ampere's loop law, and we get this formula. Outside we had already figured it out. And it's exactly the same thing you will see even over here. They have done the same thing, and you can see the same graph is right over here. Okay. Clear, guys, till this point? Now let's go to the solenoid, which is there over here, solenoid diagram. But before going to the solenoid diagram, let's solve a simple question on this. A simple question on this. A cylindrical long wire carries a current I, and the cross section has a radius capital R. Find the ratio of the magnetic field at a depth of R by 3 versus outside from the surface at a distance of R by 3. Very interesting question. Let's try to understand this. Read the question again. Just check this out. Okay, just read that question. You are at a depth of R by 3 from the surface versus at a distance of R by 3 from the surface outside, and you have to find the ratio of the magnetic fields. Okay, fair enough. So what I will do first, okay, let me just get rid of this statement. I understood what the problem is. So let's just say that this particular radius is nothing but R, which is the radius of the cross section. You are once inside, once you are outside, which means, understand this, once you are inside at a distance of R by 3, that means from the center, your distance will be R minus R by 3, which is 2R by 3. This is basically going to be 2R by 3. Depth is R by 3 from the surface. That means from the center. This is from the center. Your distance is 2R by 3. Same way, when you are outside at a distance of R by 3, that means from the center. Again, from the center. This is R by 3. Your distance will be R plus R by 3, which is basically 4R by 3. I need these things, without which I can't find the field, because all the field formulas are measured from the center. Mind it. So when you are inside, the formula looks like this: mu naught I divided by 2 pi, radius is R square, and distance from the center is just proportional to it. So here our small r is basically 2R by 3. rest of the things as it is. So R cancels and you will get mu naught I. 2 also cancels by 3 pi r. Mu naught I by 3 pi r is what is inside at a depth of r by 3. Till this point, is it clear? Everybody with me? Okay. Now let's go outside and see what the formula will be like. When you're outside, the formula changes to mu naught I by 2 pi r. So remember, we are just using this. We are just using this when you're outside versus inside, right? So when you're outside, the radius of the wire does not even matter. So this small r is basically 4r by 3, distance from the center. So mu naught I by 2 pi into 4r by 3. So 3 goes on the top. So 3 mu naught I, 4 2s are 8. So 8 pi r. That's it. Now the final answer is finding the ratio. So magnetic field inside versus outside. Many terms are common. Mu naught I, pi r, everything is common except for this number 1 by 3 and this number 3 by 8. So 8 will go on the top, 3 3s are 9. So the answer is 8:9. So the answer is 8:9. Got it, guys? How to use and apply it in the problems? This is by far the most important concept, you can say, in the application of Ampere's loop law. Many times this question and this graph or even this formulas have come. So please read it properly. Okay, very, very important. I hope you now understood how to apply these formulas. All the times, make sure that you are measuring the distances from the center, not from the surface. Else you'll get a completely wrong answer. Yep. All right. Next is a solenoid. Now, what is a solenoid? Solenoid is nothing but, imagine you take a cylinder, something like this. Now you can see this bottle is like a cylinder, and you wind a coil across it. This turn is in this plane, then here, then here, then here, then here, then here, and you make many windings across this, cylinder. This device is then called as a solenoid. When you pass current, it will produce magnetic field, something like this. So you can see there are many turns. It will produce magnetic field like this. So it will behave like an electromagnet. It will have magnetic properties. It will have north pole and south pole, and that is exactly what a solenoid is. We mean that solenoid's length is large compared to its radius. That is the meaning of long solenoid. It consists of long wires which are wound in the form of a helix, where there is neighboring turns are closely spaced. So each turn can be regarded as a circular loop, and the net field is the sum of all the fields, and they are used as basically electromagnets. And then we have been asked to find out what is the magnetic field due to such a long solenoid. They have done this small derivation over here. So we'll just figure out how they have done this derivation. All right. So done this particular derivation over here. So let's figure this out, how they have done this. All right. So starting off in a very simple manner, guys, observe this. I will explain everything very simply so that you will never be confused. This is a short solenoid. This is a long solenoid. This is a long solenoid. The difference is only how the magnetic fields will approximately look like. Here, the magnetic field lines will look like this, maybe. This is the north side, this is the south side. North because it's coming out, south because it is coming in. Whereas in this case, it will look something like this. So like you can see, The difference is how the field lines are in most of the solenoid. How the field lines are in most of the part of the solenoid. Here you can see the magnetic field inside is non-uniform. Is non-uniform. Very, very important. It is not constant throughout. Here it is weak, strong, strongest, strong, weak, weaker, and it keeps on diverging or converging. Whereas over here, you can see that the magnetic field inside is roughly constant, or basically it is nothing but uniform in nature. It is just uniform in nature. So that makes a huge difference, and we basically study long solenoids where the length is much larger as compared to the cross section. Not just that, you will also notice one thing. These same magnetic field lines, now they will go like this. They will go probably like this over here. So as you go anywhere outside, let's say here or here or here, you will see that they are hardly close to each other. So as compared to this, the magnetic field outside is negligible. This is very important assumption which comes only for a long solenoid. So these assumptions play a very important role for our further calculations. So inside the magnetic field is constant and outside the magnetic field is negligible. Is this clear, everyone, till this point? Okay. Very good. Very good. Okay. Now, in order to find that out, what I will do, I'll just take a small part of the solenoid. I'll just take a small part of that particular solenoid. So this is the cross-sectional view. So let's just focus our attention on a small part of that large solenoid. Forget the ends because most of the part of the solenoid, the magnetic field lines are uniform. So what you will see is in this part, the wires are going in, they are coming from behind and coming out from here. They are going like this, going in, coming back from here, again over here. So if I show the currents, these currents will be going in over here. These currents will be going in over here. And they will be coming out from here. These are windings, these are coils which are wound on that solenoid cylinder. Okay, circular coils adjacent to each other. They are tightly wound. They are very close to each other. This is how these crosses and dots represent wires going inside versus wires coming outside. They are all carrying the same current I. Okay. Now what I will do in order to find out the magnetic field, first of all, let's imagine those magnetic field lines. They will be something like this. It will be, remember, uniform inside. Roughly, they will be constant everywhere. Yeah. Okay. Outside there is no magnetic field, so don't have to worry about it. I will choose an Amperian path which looks something like this. Very interesting Amperian path, guys. This is my new Amperian path. Amperian path to find out what's this value of the magnetic field right over here. This Amperian path, let's say it has a length of L and this width is H. This is H, this is L, it's like a rectangle. I start going like this, go here, come back to the same point. Come back to the same point. Okay. Now, next step, let's apply Ampere's loop law, nothing great. Let's apply Ampere's law and see what exactly happened. The left hand side we know is integration of magnetic field with respect to length. The right hand side will be just mu naught into the current enclosed. Because there is one length here, one length here, one length here, one length here. Maybe I can divide it into 4 small parts. Part number 1, part number 2, part number 3 and part number 4. So I can split it up into 4 parts. So integration plus integration plus integration plus integration. This is for part 1, this is for part 2, this is for part 3, this is for part 4. This is equal to mu naught into enclosed current. For the first part, magnetic field and the length are in the same direction. So think about it. Magnetic field dot dl, and this will be nothing but cos 0. For the second part, magnetic field is perpendicular to the length. So it will be b dl cos 90. For the third part, there is no magnetic field only. So it will be 0 vector dot dl. Magnetic field outside, remember, was a big fat 0 vector. I just told you over here, outside there is no magnetic field. So for the third part, this integration will definitely become 0. Again, when you start coming in, magnetic field is perpendicular to the length. So it will be b dl cos 90. And don't we know what cos 90 is? This cos 90 is nothing but 0. Even this cos 90 is nothing but 0. So this is 0, this is 0, this is 0. Only this term remains. So there will be basically 3 zeros, 0 plus 0 plus 0. Only this term remains. B comes outside. It will be just integral dl for that first part. Integral dl for the first part. So dl plus dl plus dl plus dl plus dl plus dl till here will be the total length of it. So it will be just this L and B into L on the left hand side. So that's what the LHS would look like. Everyone clear how we have used Ampere's loop law for the left hand side right now? They have not yet solved for the RHS. This is only the LHS. Yep. Now let's go to the right hand side. Enclosed current. Be careful. Enclosed current means only this much. Only how much is enclosed over here. Oh, I need a parameter. Of this solenoid, and there is a very important parameter of a solenoid which is called as the number of turns per unit length. This is how many turns are there. This is basically how many turns are there upon the length of the solenoid. This is small n. This is number of turns, and this is the length that you have considered. This is again a very important formula which is generally given to you. This solenoid has 1000 turns in 1 meter. So very tightly wound. This solenoid has 3000 turns in just a meter. So very, very tightly wound. So number of turns per unit length is small n. Total turns is n. The length which is considered is basically L. This will help me find out how much current is there over here. So think about it. There is current I. There is current again I over here. Again current I over here. Like that, there will be so many currents. How many such currents will be there? 1, 2, 3 till basically n. So the total current which you are talking, which is like enclosed current, will be nothing but I enclosed. This particular I enclosed. Won't it be I multiplied by n times? I plus I plus I plus I. How many times? N times will it be there? Everyone fine till this point? But what is n? What is n? N will be small n into L. Small n into L. So therefore, won't this be small n multiplied by length L? So just put that over here. I into n into L. So mu naught small I into n into L. Obviously what happens is this length and this length gets cancelled, and I am just left with magnetic field inside is mu naught small n into the current. That's it. That is our formula. That's exactly what they also would have got. Mu naught Ni. Yes. See this? Mu naught Ni. Is this clear, everyone? How we got this? Very, very important. Shall we go ahead? Yeah. So you should remember this formula. Permeability into number of turns per unit length into current is the magnetic field inside. Outside, like I said before also, there is no magnetic field for a solenoid. So I think the question slide is missing somewhere. But anyways, let's go directly to the question. This is a NCERT exercise. A solenoid of certain length has a radius of 1 centimeter and is made up of 500 turns. It carries a current of 5 amperes. What is the magnitude of the magnetic field inside the solenoid? That's the question. That's the question. Let's do this. The number of turns per unit length is given, okay, or if we have to find it out, current is given, find the magnitude of the magnetic field inside. So you just have to use the formula B is equal to mu naught Ni, but N is not known. So how do you find number of turns per unit length? Radius, I think this is useless information. Length is useful and number of turns is useful. This piece of information is useless. What will I do with the radius? What will I do with the radius? It is not needed only to the problem. So 500 divided by 0.5 will give me 1000 turns are there in a meter. Next, magnetic field is mu naught Ni. Mu naught is 4 pi 10 to the power minus 7. Number of turns is 1000 and the current, which is I, is given to be 5 amperes. That's it. It's multiplied, you get the answer as 6.28 millitesla. That's the magnetic field inside. Outside, naturally, it will be 0. The only job of the radius over here is for you to visualize. Radius is 1 centimeter, length is half a meter. So it is, yes, a long solenoid, which means the formulas that we derived over here are valid. Because all these formulas are only for long solenoid and you do not get short solenoids in your NEET examination. Is that okay? That's the significance of that radius. Otherwise, it was not used at all in the calculations. Yep. Shall we go ahead to the next concept, guys? And that is basically force between the parallel wires, and then we'll come to the torque part of it also. Shall we do this? Where is it? Yeah, force between wires carrying current. Start reading this, and meanwhile I'll also drink water. Thank you for reminding me. Okay, let's do this. See, if you have a wire which carries current, obviously it produces magnetic field around it. We also know if a wire is placed in somebody else's magnetic field, it experiences force, IL cross B. So if I have two wires nearby each other, this guy will produce a field, this guy will be affected by the field. Not just that, even this guy will produce a field and this guy will get affected by it. So basically, two wires carrying currents, if they are placed near each other, what will happen? They will exert action-reaction forces, Newton's third law. They will exert magnetic forces on each other. They might end up attracting or they might end up repelling each other. So we are interested in calculating how much this force is. We are interested in calculating how much this magnetic force is. Okay. So basically, yeah, we have learned that there exists magnetic field due to current carrying wire. Further, we have learned external field will exert force. So these were the two initial statements. Magnetic field is there due to a current carrying wire. Also, external magnetic field will exert force on a current carrying wire. So from this, it is expected that two current carrying wires near each other will exert magnetic forces on each other. This is what we are interested to study. And then they have done this calculation part, and then they say this is also used for defining Ampere's loop law and all of that. So we'll come to it. Let's understand it first. Okay, let's draw two wires, guys, first. Let's draw two wires. This is one wire, and this is another wire over here, placed at some distance from each other. Let's say that distance is basically D. Let's say this wire carries current I1. Let's say this wire will carry current I2. Now you can do the same logical thing when the currents are not in the same direction. Maybe like this. They are opposite to each other. Now they are same direction. So each wire will produce a current, will produce a magnetic field around it. So let's say the magnetic field produced by this wire will be like this. Try to visualize this now. Something like this. If the current is in this direction, the magnetic field lines will be like this. So if I probably show it at the right place. Okay. Now, obviously the magnetic field lines will be like this. Magnetic field lines will be like this using right hand loop law. And you can see the current is here. The fingers are curling this way. So at this point on the second wire, the magnetic field line is basically going downwards. So this is the basic direction of the magnetic field at this particular point on this second wire. This magnetic field is given by mu naught, current number 1 has produced it, divided by 2 pi distance. Distance is nothing but d. That's the magnetic field. Now please remember, this magnetic field is definitely perpendicular to the length of this wire. Okay. So if you ask me how much is the force, I will use IL cross B. Length is here. Cross product it with the magnetic field. Length cross B will go this way. That means my force will be like this. That means my force will be like this. Do not forget that our force is given by current which is going, which is basically in this case I2, into the length which is, let's say, L, and cross producted with the magnetic field of this guy. So cross B, IL cross B. So if you ask me how much is this force, magnitude wise, current is just I2 only, there is no change in that. Length is, let's say, L. Magnetic field, I just figured it out right over here, which was mu naught I1 divided by 2 pi d. Shift the length below, shift that length below, I will get force per unit length is nothing but mu naught I1 I2 divided by 2 pi d. Divided by 2 pi d. That's it. I have got the force per unit length. If you do the same analysis for the second wire, which is also producing magnetic field again, and then you find the force on the first wire, it will be exactly in this direction. It will be exactly in this direction. Obviously, these two forces will be equal. This force per unit length on basically both are equal. They are equal and opposite. This is using your third Newton's law of motion. Newton's law of motion. If the direction is same, it is attractive. Naturally, if the direction is opposite, what will happen? It will be repulsive in nature. So the forces will try to repel the currents. So same will attract, opposites will repel. Exactly opposite of electrostatics. Exactly opposite of electrostatics. Not just that, if I play around with this, F by L is again mu naught by 2 pi I1 I2 divided by 2 pi d. Say for example, if I rearrange this and I write I1 I2 as F by L, I1 I2 is F by L, and then I write 2 pi d on the top divided by mu naught. Mu naught is nothing but 4 pi into 10 to the power minus 7. This will cancel, this will become 2. So I'll just get F by or Fd by L multiplied by 2 into 10 to the power minus 7. Now this helps me define something called as the unit of current. If you remember, SI unit of current is amperes, and amperes is a fundamental quantity. Charge is not, charge is the derived quantity. So this is used to define the ampere, which is one of the fundamental quantities. That is what they have told. This is used to define ampere, which is the base unit, the fundamental quantity. And like I said before also, parallel currents will attract and anti-parallel currents will repel. Okay, this is exactly opposite in electrostatics. Same things would repel, opposites would attract. Here it is opposite in magnetism. Same will attract, opposites will repel. Now, how is it used to define the unit of current? Basically, if you end up passing some current which is same in both of them, and the distance between the wires is, if for example the distance between the wires is 1 meter and the same current is passed in both of these wires, and you find out that the force acting per unit length exactly happens to be 2 into 10 to the power minus 7 newtons per meter. So F by L is this value, this and this will cancel, distance is 1 meter, then I1 and I2, the product of it, then I1 and I2, the product of it will be 1, and since both of them are equal, I square will be 1 or I will be equal to 1. This current is then 1 ampere. So the current which you pass equally in both the wires for a separation of 1 meter, producing a force per unit length of 2 into 10 to the power minus 7 newtons per meter, that current is basically called as an ampere. That's how the unit has been defined. That's how the unit has been defined, and that's exactly what they have done over here. Ampere is that value of that current which maintained in each of the two very long wires, so that they are 1 meter apart and they will produce a force of this many newtons per meter. That is a ampere. Exactly what I have done over here. Is this clear, everyone, how this came? Give me a thumbs up, then we will go ahead. Give me a thumbs up, then we'll go ahead. Okay, all right. So, charge is basically a derived quantity. Remember, we have done this in electrostatics. Charge per unit time is current. So, charge is basically current into time. So, ampere into second. So, basically, ampere multiplied by second is nothing but a coulomb. So, that's how coulomb comes into play. Okay, that's how coulomb comes into play. Very simple, very straightforward. All right, let's go to the next thing, which is the torque on a current carrying loops and magnetic dipoles. And for this, they have given one diagram and they have derived something and they have found out the torque on it. And they have told that, you can change the orientations, etc. And then you can get some formula. Okay, let's understand what they have exactly done. So say for example, Okay, so this is basically a current carrying loop like this. And let's say it is placed in somebody else's magnetic field. Maybe the magnetic field lines are like this. For example, and let's say the length of this wire is L. This is also L. Let's say a square loop is there. It's placed in this magnetic field. So let's find out what are the different forces acting on such a loop of wire. This is a loop of current carrying wire in an external magnetic field. One thing I know for 100% guarantee, that is the net force acting on any such loop will always be zero. How do I know this for so sure? Because we have done this in the previous lecture. Net force is always zero on any loop which is placed in a magnetic field. If you have forgotten, no issues, I will show it to you. Right over here we have done this. Where did it go? The force acting on it. My God. Yeah, here. The magnetic field is passing through this loop. It is uniform. The net force on a loop is always going to be zero. This is something which we had concluded even in the last lecture. All right. So as long as it is a loop, doesn't matter which shape, square, circular, hexagonal, the net force on it will always be zero. So that is for sure. But torque may not be zero. That is exactly what we need to find. So if you consider this segment, this segment, this segment, and this segment separately, and try to find individual forces, and then maybe torque can be calculated. So let's do this. For this part, magnetic field is here, length is here. Length cross B will go down. Just like for this guy, length is here, length is towards you, magnetic field is there. Length cross B will go upwards. So try to do this by yourself using your hands. This wire is coming towards you. This wire is going inside the plane. So on this, the force will be here. On this, the force will be downwards like this. Try to visualize. All right. It will be like this. Just check this out. Are you able to visualize these two things? Okay. Length is going inside, magnetic field is there. So length cross B will go down. Here length is here. So length cross B will go up. What about this part and this part? L cross B will be 0. L cross B will be 0 because length is parallel to the field. So no force on them. So here the force will be 0 and on this also the force will be 0. Each of these forces will be current carrying through this particular wire. Let's say I call it as I. So it will be I. Length is, let's say, L, and into the magnetic field. Even same thing over here, guys. This force will also be again nothing but current into L into B. If you are wondering what happened to sine theta, well, it will be sine 90. Sine 90 is 1. Why 90 degrees? Because you can clearly see magnetic field is here, current is here, they are perpendicular to each other. So that's the reason why it is sine 90. Now, what happens? These two forces are equal opposite, they cancel each other out. That is why you can see net force is anyway 0, but they will definitely produce a torque. They will definitely produce a torque. One of the force is here, the other force is here, and the separation between them is this, which itself is nothing but the length of that loop. So what will happen? There will be definitely a torque which will be produced. There will definitely a torque which will be produced over here. How much will be the torque? Well, if I measure the torque about the center, if I try to measure the torque about the center, it will be R cross F, that means L by 2 into F, plus R cross F, again L by 2 into F. Each of the force is giving a clockwise torque, so that's why plus. This force is trying to rotate it clockwise. This force is also trying to rotate it clockwise, so that is why plus, else this would have been minus. So it will just be L into F. L is L only, okay. F is whatever I wrote over here, which is nothing but I, L, and then you have B over here. Now I'll just play around with this a little bit. I will just write current as it is. L into L is nothing but L square, and then magnetic field over here, and then this is basically your torque. Now, next step, I will think what exactly is L square? What exactly is L square? L square is nothing but the area of that particular loop, is nothing but area of that particular loop. Is that right, everyone? And magnetic field is basically as it is. Now, I think further, okay, if this is the scenario, then just imagine if by chance there were many turns, if by chance there were many turns in that same loop, something like this, okay, if there were many turns, if there were n number of turns in that same loop, then what would exactly happen to this particular formula? This torque will be for a loop, therefore for n number of turns, the total torque that you would have got, will be n times of this. Each one of them will get the same torque. So that's why this will be I, area of the loop, but multiply everything with n. So n current into area of that particular loop, and that magnetic field is there. Got it, everyone, till this point? Very good. Now we know that torque is a vector quantity. We actually know torque, strictly speaking, is a vector quantity. Somehow can I find if the torque can be represented in the vector form? So then you will think, okay, torque is basically, we just saw over here, it is clockwise, that means it is going like this. That means the torque vector itself, will be like this. The torque vector itself will be like this, because it was clockwise means it will go that way, my bad. So the torque vector was this way. The torque clockwise, so it will go inside the plane of the board. But the magnetic field is here, so 100% it is not parallel. So maybe there is some other relationship over here. So what I do now, this NIA, which is there, number of turns into current into area, I write it as a new quantity, but as a vector quantity called as M, which is called as the magnetic moment. This B is as it is. This will then become the torque, where our M, which is number of turns into current into basically area of that loop, is called as the magnetic dipole moment. It's a vector quantity. Where is this vector? If the current is going like this, curl your fingers in the direction of the current. The thumb will point in the direction of the magnetic moment. The reason for that to happen is because Observe this carefully now. This is our loop. The magnetic moment will be perpendicular to that in the direction of the thumb when you wrap your fingers in the direction of the current, because you will notice very clearly that one side will be north, this side will be south, dipole, so it will have a dipole moment, hence magnetic dipole moment M, north pole and south pole. So this coil is like a bar magnet which is inside. So that's why magnetic dipole moment. Is this clear? So this is a new quantity which we have defined called as the magnetic dipole moment. So now this reminds me of electrical dipole moment into electrical field is torque, but this is a very special case. If you notice, the magnetic moment was up, magnetic field was here, so the angle between them was 90 degree. So maybe whatever was there in this scenario, magnetic moment was on the top, magnetic field is over here, whereas the torque which is there, it's inside the plane of the board. So clearly the angle between magnetic moment and magnetic field was 90. So whatever was multiplied here was 1. This 1 means actually it is sine of 90. So MB sine 90 was there, and whenever sine comes, it should be a cross product. Hence our torque in the vector form should be technically magnetic moment cross our magnetic field. Cross our magnetic field. This is very, very important. This is the torque which is acting on a loop carrying current. It is M cross B. As simple as that. This is the derivation for that. It's just like electrostatics. It was P cross E. Here it is M cross B. That's exactly what they have mentioned. They have done the same derivation over here. Okay, for that same loop. Okay, and they have said that, you know, this is very similar to electrical dipole moments torque. So all these are, you know, very important things. Okay, so magnetic moment of the current loop is this, where the area vector is given by the right hand thumb rule and directed into the plane of the paper as shown. This is just like electrostatics case. Okay, and then they have given some things over here. Magnetic moment is NIA. Okay, right. Now, just like in electrostatics, here also, say for example, first our loop is, let's say, like this. Then let's say our loop is like this. Then let's say our loop is like this. I'm shading the area so that you can visualize it even better. This is the area of the loop. It has some number of turns. So the magnetic moment in each case, let's say first time it is here, next time it is here, next time it is here. These are magnetic moments of that current carrying loop. Magnetic field, first case it is here, second case it is here, third case it is here. Magnetic field. In the first case, the angle between magnetic field and magnetic moment is 0. Here the angle is 90 degree. Here the angle is 180 degrees. If you ask me what the torque is, sine 0 is 0, it will be 0. Here sine 180 is also 0, so it will be 0. Here the torque will be MB sine 90, which is 1. So this torque is actually the maximum torque, and this torque will try to pull it like this. This torque will try to pull the magnetic moment in the direction of the field. Here, because the torque is 0 and anyways force was always 0, force is 0 always. Whenever force and torque both are 0, such as the condition of something called as equilibrium. So this is definitely in the equilibrium condition when angle is 0, the torque and force were 0. Even this is the condition for equilibrium. This is also in equilibrium. This is not, because torque is there, it will definitely rotate. The coil will spin for sure. Got it? But you know, this equilibrium is actually stable equilibrium. Yes. Whereas this equilibrium is actually unstable equilibrium. The reason for its instability is if somebody disturbs the magnetic moment either here or here with respect to the magnetic field, the torque here will, oops, sorry, my bad. Somebody disturbs the magnetic moment here or here with respect to the magnetic field like this. The torque will try to bring it like this or like this. So earlier it was in equilibrium, you slightly rotate it, the torque will immediately flip it over here. So it is not coming back to its original state. That is why it is unstable. Whereas over here, if you slightly move it up or slightly make it go down with respect to the magnetic field, you will see the torque will immediately try to bring it back. It will try to restore it back. So because it tries to restore, it is stable. Here also it was equilibrium, but if you disturb it, then gone. It will immediately flip onto the other side. Is this logic clear, everyone? Yes. Why opposite in electrostatics and magnetism? There is no real reason for it. It's just how things are happening as a coincidence. Like even electrostatics law is K Q1 Q2 by R square. Gravitational law is G M1 M2 by R square. So, you know, there is similarity in gravitation and electrostatics. So maybe when God made this universe, it's like probably, you know, he had to write or he had to make things with a mind, as in like, okay, I made this, okay, I had this idea in mind for gravitation, so I'll make this for electrostatics. He just changed the numbers, he just changed the constants, or he just changed the values, that's all. But formulas were looking very similar. It's like a group assignment. Everybody is doing the same thing but changing the values. So maybe the universe was made like that, but each force was made by a different individual, or maybe just done again and again. So you don't want to repeat the same thing, but you have the same ideas, so you're just copying it. Who knows? We would never know. All right, cool. So that is what is important over here. Now let's go to the next point, which is circular loop as a magnetic dipole. And this equation might look confusing at times. So let me go back to this particular page. Field due to a coil. Remember, I told you here, a field which is generated by a coil carrying current looks like this. And this looks very similar to a bar magnet's magnetic field lines. So this is exactly what we are trying to study. And we had derived an expression over here, which was like this. So let me just copy this over here. Wow, this is going to take a while. I think I might as well have drawn this now, I feel. Anyways. Now, we have also seen that it produces magnetic field lines like this. and this looks very much similar to just a bar magnet with south pole and north pole. Field lines are coming in a very similar fashion. And they continue. It's not like they don't. They continue even inside that magnet. They continue even inside that magnet. They are very, very similar. So is there some relationship? The answer is yes. So let's find that out. What is that relationship? So if you basically, go really far away, if you go really, really far away, then what happens is, oops. So if x is much, much larger than the radius, that means the loop is over here and you are somewhere over here. The x is much larger than the radius on the axis. Then what happens is that this number will be very large, this will be very small, r will be very small. So you can neglect it, and hence this same formula for the magnetic field along the axis will become, because this will then become negligible in front of whom? Who will it become negligible in front of? X square. So the formula will become, see this, mu naught is there, 2 is there, this current is there, r square is there, of course. This has become negligible in front of this, so it will be x square only. It will be x square only. The whole thing raised to 3 by 2. Whole thing raised to 3 by 2. Correct? Now 2 and 2 cancels, it will just become x cube. So it will just become mu naught by 2. You have just I r square on the top, and below you just have basically, what is it? X cube over here. Now current into r square is for a single loop. Let's say the same thing was done for multiple loops. The same thing was done for multiple loops. Let's say, there are n number of turns over here. Let's say there are n number of turns over here. So if you had n number of turns, what would have happened? I would have to multiply it with n. I would have to multiply it with n. I would have to just multiply it with n. Right? That is the only difference. Okay. Now what I will do, I will just multiply and divide by the number pi. So what will happen? This will become mu naught by 2 pi. And then over here I have n I pi r square. And this whole thing divided by x cube. Notice what happens. N I pi r square, N I A, number of turns current into area of that loop. What is it? That is nothing but the magnetic moment. Then instead of mu naught by 2 pi, how about writing it as mu naught by 4 pi? Just put that number 2 on the top. Anyways, it is the same thing. And now write down x cube over here. I will get the magnetic field on the axis. This formula looks very similar to, observe this carefully now, observe this very carefully. If you had a negative charge over here and a positive charge over here, minus q plus q, which will now create an electrical dipole moment, and you go on the axis at some distance, which is really far, the electric field on the axis is given by 1 by 4 pi epsilon naught 2 into you had electrical dipole moment divided by whatever distance you went divided by x cube. Exactly similar. Here you have the constant in electrostatics. Here this is the constant in magnetism. 2 is there here, 2 is there here. Electric dipole moment, magnetic dipole moment, x cube, x cube. So the formulas look very similar. So this proves that a current carrying loop is actually like a magnetic dipole. This proves a current carrying loop is actually like a magnetic dipole with polarities of north and south. The formulas are very, very similar. Yes, Krishna, our national flag color has come. Looks exactly. I was getting the same feeling. Saffron, green, white, naturally looking Indian flag. So we have got Indian flag in Shreyas Sir's class before GTA 6 in magnetism, and that too in such a nice way. Beautiful. Same, but different. Very good. Excellent. So that is what they have mentioned over here. So this is similar to this. This is basically similar to this. This result becomes exact point magnetic dipole. Shown that any loop. Yep. This is the analog of electric dipole moment. Electric dipole moment is made up of two charges. In magnetism, very important, a magnetic dipole is most elementary element of equivalent charges. But remember, magnetic monopoles do not exist. Although we wrote it's like a magnetic dipole with two polarities, but remember, you cannot ever separate the north pole and south pole separately, unlike electricity, where positive and negative can be obtained separately. Okay. So we have shown, what is the final conclusion? We have shown that a current carrying loop produces a magnetic field and behaves like a dipole, which is basically north-south bar magnet. It behaves like it. It is also subject to torque. It will also experience torque like a magnetic needle. We know this. If you take a magnetic needle with north and south polarities and you place it in somebody's field, it will definitely experience a torque. Definitely. Yeah. And also, there are no magnetic monopoles. Yep. No magnetic monopoles. These are the final conclusions. Till this point, all this theory is understood, guys. All right. This is exactly what they have done over here. Okay. Neglecting X is much, much larger than R, etc. So the same derivation, I have done it for you in a much simpler manner. Okay. Let's go to the final topic, and that is called as the moving coil galvanometer. Moving coil galvanometer, and they have given the construction, the working, and how do we use it as a voltmeter versus how do you use it as a ammeter. Okay, that is the last part of this. So moving coil galvanometer. Galvanometer is nothing but a device to sense if there is current, if it is passing in this way or opposite way, and if there is no current also, it will show me. It's basically a sensitive ammeter or a sensitive current measuring device. It's very sensitive. It can't measure a large amount of currents. And it works on the principle of magnetism. There is a wire which is wound. It forms a coil. Current passes through it. There are magnets inside. The coil will move. So the needle moves on that scale. And that's how you can measure everything. So basically, a moving coil galvanometer, whose principle is understood on the basis of the discussion previously. It consists of a coil. Yeah, a galvanometer basically consists of a coil with many turns, free to rotate about some fixed axis in a uniform radial magnetic field. There is also a cylindrical soft iron core which makes it radial. Okay. And when the current flows through the coil, there is a torque which acts on it, and based on that torque, you basically measure everything else. Okay, since blah 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 blah, resulting in a steady direction. This where K is the torsional constant of the spring inside, and from that you basically get this formula. The quantity in the brackets is a constant for a given galvanometer. It can be used in different ways. A galvanometer can be used in different ways. It can be used as a detector to check if current is flowing in the circuit. And example, Wheatstone's bridge, blah, blah, blah. and it can be also used as an ammeter to measure the value of the current. Okay, and also it can be used as a voltmeter to measure the voltage across a given section. So construction, working and applications, all of them one by one. Let's start by the construction part. Let's understand this, what exactly happens. Everybody pay attention. Everybody pay attention first. So say for example, if I have a horseshoe magnet, okay, if I have a horseshoe magnet, something maybe like this. If I tell you this is the North Pole, this is the South Pole, then what will happen is magnetic field lines will go from here. Probably they will come here. Some of them will go from here, will come here. Definitely. Some will go like this. Some of them will again go like that. And they will come back over here. This is how the magnetic field lines will roughly look like for a horseshoe magnet. Imagine I take a cylindrical magnet, meaning it looks something like this. You have to visualize it a little bit. It is a cylindrical magnet, guys. It's a cylindrical magnet. So something like this. Imagine it's like the horseshoe magnet, but the polarities have come very close and it has been scooped out. Instead of flat surfaces, a scooping out has been done, as if you can fit an imaginary cylinder inside of it. Just imagine you can put an imaginary cylinder inside of it. So you have taken out a cylinder outside. Are you able to visualize this? Are you able to visualize this? What is the meaning of the shape? Just check this out. Yep, very good. So now what we will do, how will the magnetic field lines look like? The magnetic field lines will look very interesting, going from the North Pole to the South Pole, maybe something like this, maybe going like this, maybe going like this, maybe even going like this. And outside of it, there might be some stray magnetic field lines. That's ignored. We are just interested here. Mainly, what happens is, if I look at it from the side angle, very important, I will see the magnetic field lines doing this. Doing this. This is from the side angle. This is from the side angle. This is North Pole and this is South Pole. This is how the magnetic field lines will look like for cylindrical magnets. What are these magnets called as? Cylindrical magnets. Cylindrical magnets. Cylindrical magnets. This was your North Pole. This was your South Pole. Now this field is very interesting because, see, the magnetic field lines go like this, they turn. The magnetic field lines go like this, they go straight. They go like this and they turn. Approximately at the center, they are concentrated, and it feels like if you ignore the central part, if you just ignore the central part for most of the practical purposes, observe this carefully. Ignore that central part. If you just concentrate on the ends, it feels as if the magnetic field lines go here, observe this now, go like this, 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 and they come back over here, probably they come back over here, probably they come back over here, over here, over here, and of course over here. It feels as if it is like this. Ignore this part. Doesn't it feel as if, the magnetic field lines are, just continuing over here? They're just continuing on the other side. It just gives you that notion, isn't it? It feels like they're just continuing over here. So guys, this kind of field is called as a radial field. What is this called? Radial field. Radial field means the magnetic field lines are, along the radius of that particular circle. So when this happens, a very interesting thing, occurs. So imagine you are in a radial field. Imagine you are in a radial magnetic field. So there is magnetic field line here, there is magnetic field line here, there is magnetic field line here, there is even magnetic field line here, like this. So this is your radial field. And now in such a radial field, you are placing a coil. You are basically placing a coil. Now, no matter how the orientation of the coil is, observe this carefully now. No matter what the orientation of the coil is, you will see that their magnetic moments, let's say in this case the magnetic moment is like this, in this case the magnetic moment is like this, in this case the magnetic moment is like this. Every time you will see that the respective magnetic moments are, in the plane, the coil is in such a plane that it experiences the force due to these magnetic field lines. This magnetic field line which is there, it's in the plane of this particular coil. It's acting on this magnetic moment and they are always going to be perpendicular. Same way, when you take this particular loop, it is this magnetic field line which affects this particular loop, which is having this magnetic moment. Again, this magnetic moment is being affected by this magnetic field. Every time the magnetic moment is perpendicular to the magnetic field. That means theta is 90 degrees. That means the torque, which is mb sine theta, it will be mb sine 90, which is just mb. And this means the torque is constant for all the orientations. Is this absolutely clear? This is one of the most critical criteria for a moving coil galvanometer. Every orientation, it will experience the same torque. Very, very important. Okay, keep that in mind. So, just reiterating it over here. This was our coil. Visualize this particular plane. Other magnetic fields will not play a role except for only this magnetic field which is passing. Other field lines are passing through some other plane. Don't worry about them. So only this magnetic field will play a role and it will affect the magnetic moment of that coil that is perpendicular. and it is always going to be perpendicular. You take any orientation, you will find some or the other magnetic field line which is in the plane of the coil or perpendicular to that magnetic moment. Now what happens is, imagine you take any object and you connect it to a twisted spring. This spring can be twisted like this, so you can turn this object like this. So you twist it by some angle, let's say theta. The spring gets twisted, because of which what will happen, it will experience a torque which will try to restore it. So there will be a restoring torque. This torque is found to be proportional to how much you have twisted it, and that constant is K. Again, that constant is K. This torque is some K into theta. This K is called as the torsional constant of the spring. Torsional constant of the spring. Why not spring constant? Because spring constant is when F is kx. This is displacement in meters, this is in Newton. When you have Newton per meter torque and radian, this is torsional constant whose units is Newton per radian. Is this clear? This is torsional constant. How many Newton meters of torque is needed to rotate it by 1 meter? That is torsional constant. So when you twist something, it will try to restore it back. When you twist something, it will try to restore it back. Which means now, just imagine you have a coil, okay? Imagine you have a coil, let's say like this, and it is placed in between, it is now placed in between cylindrical magnets. It is now placed in between cylindrical magnets. This coil will generate its own magnetic moment, and there is obviously some magnetic field, of course, over here. There is some magnetic field over here. Let's say I call it as M, which will definitely produce some kind of a torque, Sorry, this is not M, this is B. Magnetic field. So there was a torque now. So because of the torque, it will rotate, but I want it to stop. So that's the reason why I have taken this coil and made sure that it is connected to a spring like this, which will then get twisted by some angle theta. And when it twists, it will apply a restoring torque. Like this. And this loop will be in equilibrium. It will be in equilibrium if the restoring torque by the spring, which is trying to bring it back, is exactly balanced by the torque this way by the magnetic field. The magnetic field is producing a torque like this, is trying to rotate it, and at the same time, the another torque is trying to bring it back. This torque by the spring is nothing but K into theta. This torque by the magnetic field was just MB. M is nothing but number of turns into current into area, and this is B. This is just K theta. Think about it. If current increases, theta increases. If current reduces, theta reduces. Current becomes 0, theta becomes 0. Is that clear? So more the current, more is the deflection. So therefore, our theta will be NBA divided by K, and this is current. Very important formula. So you can see the deflection is directly proportional to the current passing through the coil. This is important functioning of the galvanometer, because when you see a galvanometer, right? When you see a galvanometer, what it has is basically a scale. Let's say this is 0 like this, and also on the other side. And then there is this needle which will deflect, and this particular galvanometer, some current is passed in, some current comes out, some current is passed in. This is the current passing through the galvanometer. There is obviously some kind of deflection that happens, theta. This theta is proportional to the current passing through the galvanometer. More the current, more the deflection. No current, no deflection. Got it? So this is exactly how current is measured using a galvanometer. You see how much is the deflection. From this, you can find the current through the galvanometer. Now, number of turns, field, area and spring constant, obviously they are constants together. So these parameters will never change for a galvanometer. It will be always the same. It will be always the same. Is that okay? So N, B, A and K all will be the same, and very easy to remember this. NBA is associated with basketball. So just imagine your basketball, imagine your basketball which is there. It's being thrown, not thrown, actually it has been kicked by your Pandu. Your Pandu does not know how to play basketball. So what he has done, he has kicked it. He has kicked that basketball, so that basketball goes inside the basket. So NBA is associated with basketball. K is kick. Where do you kick from? Below. So K is below. K for kick. When you push it by hand, hand is on the top, numerator. K is kick. Kick is below. So basketball has been kicked by Pandu. So current is, over here. Deflection is over here. That's how you remember it. Got it? Everyone? Oh yes, Sumi, definitely. I'll take water. Thank you so much for reminding me. Now this constant NBA by K will be how much deflection is there per current. This is called as the sensitivity of galvanometer. Basically, how many radians is deflected per unit ampere. For an ampere, if it deflects more, it has more deflection. Is that okay? Keep that in mind. Now remember, always any instrument can measure a maximum value. So there will be obviously a limit till which it can measure. So say for example over here, if this was obviously your theta, there is a maximum limit till which you can measure it, and that is only till here. So what you get over here is theta max, maximum deflection. So full scale deflection is basically theta max. So there is obviously maximum current which can be passed through the galvanometer. That will be I max, also called as a full scale deflection current. So if the current is more than the full scale deflection current, the galvanometer may spoil. It may spoil, or it may burn, or it may be irreparable. So that is why you try to maintain the currents within the limits, within the deflection of the maximum value over here, else the coil will definitely burn. Yes. Next important thing that you need to remember is that a galvanometer also has its own resistance, This is also called as the coil resistance. This is also called as the coil resistance of that particular galvanometer. So any galvanometer has a resistance. Obviously, it is made up of many windings, like I told you over here. It's made of a coil. So definitely it has some resistance, and it can only measure a limit of the current, which is not too much. So you have to make sure the currents are well within the full scale deflection limits. Are all these pointers clear, my dear students? Shall we go ahead? This was your sensitivity of the galvanometer. This was maximum current, which is Imax, and this is your coil resistance of the galvanometer. All these are important parameters. Okay, so that is exactly what they have done over here. If you realize, okay, this is exactly what they have done. The torque, the derivation, everything. Deflection is NBA by K into current. This is the constant for a galvanometer. It can be used to check if current is flowing or not. Do you remember Wheatstone's bridge? 4 resistors are placed. You place a galvanometer. If the potentials are equal, no current will pass. No current, no deflection. So that is why null deflection method. So when there is no deflection in the Wheatstone's bridge, no current is passing, and you can say R1 by R2 is R3 by R4. That is what we have studied in Wheatstone's bridge. So that is one of the first application to check if current is even there or not there. Okay. Next important thing, it can be also used to measure the value of the current in a given circuit, which is basically an ammeter, and the second usage is as an voltmeter. So what is this? How do you use it as an ammeter versus a voltmeter? So let me give you a very simple example. Just imagine there is a road which goes inside your neighborhood, okay, and if there are few cars going in it, then it's okay. But if many cars are going, many vehicles are going, it becomes crowded, it becomes like a traffic jam. The road cannot handle too much. So same thing also happens in your blood vessels. If there is a blood vessel, too much of blood is going through that vessel, the blood vessel can't handle it, or maybe there is some obstruction here, there is a limit till which the blood can go. So what you do is basically you bypass that movement of vehicles or the blood or whatever has to flow through another tube, through another road, through another path, so that this part remains unaffected. You basically bypass the flow. Got it? That is also called as bypass surgery, etc. Everybody clear till this point? So same way, just imagine if my galvanometer can't handle anything more than some few milliamperes, but I want to measure 7-8 amperes of current or 50 amperes of current, then I can't pass such heavy current through the galvanometer. So I'll be like, okay, galvanometer, no issues. I will do one thing. Whatever current was coming from here, I will bypass most of the current. Over here, and again let it mingle on this side. That's okay. Let it mingle on this side. And I will pass very little current through you. So if the total current was I, most of the current will flow here. A very small current will flow here. This would be probably Ig. So naturally this would be I minus your Ig. That is the current which will go through here. And this current which is passing over here will have to pass through a resistance. This is in parallel. This is also called as the shunt resistance. Shunt means parallel. This word means parallel. So this resistance has to be chosen in such a way that this galvanometer does not get burnt. So then indirectly I am measuring the current. Indirectly I am measuring the current. So that is what is the principle of an ammeter. So this thing, if it is packed inside a box, if this thing is packed inside a box, this then is called as your ammeter. So ammeter is nothing but a galvanometer connected in parallel to another resistor. That's it. So if you buy a galvanometer in the market in an electronic shop for 500 rupees and somebody sells you an ammeter for 2000 rupees, that means you have become one fool, because there is no difference as such, in a galvanometer and ammeter except for one resistor, and the resistor you can get it for 1, 2 rupees, 5 rupees. So take a galvanometer, connect a resistor in parallel, automatically it has just become an ammeter, because now it can measure heavy currents. It will bypass most of the current through it. Got it? Very good. Now usually the shunt has to be very small resistance. So remember this. So the shunt resistance is usually very small. So because of which, think about it, the resistance of the ammeter is also very small, and an ammeter is always connected in series with the circuit. In series with the circuit. Ideally, an ammeter has 0 ohm resistance. Ideal, but in reality, it can definitely have some resistance value. Ideal ammeter has 0 resistance. The symbol for ammeter is just this. You can use this or just this. This is also the symbol for ammeter. So an ammeter is actually a galvanometer plus a resistor in parallel. So just use our regular formulas of series parallel. You will get all the required data. This is the resistance of the galvanometer. There is some current entering. You bypassed it through a shunt resistance like this. This current was I. This is I minus Ig. Over here, this is basically Rg. That's it. So now, because they are in parallel, obviously the voltages are same across both the resistors. One is galvanometer, another is the shunt resistance. Voltages will be same. So I can write V is equal to current through the, this was Ig. Current through the galvanometer into galvanometer resistance, or I can also write it as I minus Ig into shunt resistance. So therefore I minus Ig into shunt resistance will give me current through the galvanometer into galvanometer resistance. Usually this is given to you, or this is given to you, this is given, and one of the things you have to find. So this is very simple equation. Don't sit and by heart it. Don't say that, sir, I minus Ig into Rs is equal to Ig into Rg. No, don't by heart it. Just remember there are two resistors in parallel. So what will be same? Voltage will be same. So voltage is IR. That's it. Don't break your head over it. So say for example, a galvanometer of let's say 10 ohms, okay, or a galvanometer of 100 ohms with a maximum full scale deflection current of just 1 milliampere has to be converted into an ammeter up to for example 2 amperes. Find the shunt resistance to be used. Find the shunt resistance which has to be used. Let's do this question. It's not at all difficult. Show the galvanometer as a normal resistance, 100 ohms resistance. That is your galvanometer. The maximum current which can flow over here is 1 milliampere. That means 10 to the power minus 3 amperes. But you can't allow that much current to flow inside. The actual current which has to go is 2 amperes. So you bypass the current through a shunt resistance, which I do not know. How much will this current be? It will be 2 minus 10 to the power minus 3. Guys, 2 is a very large number. 10 to the power minus 3 is a very small number. So won't it be approximately 2 amperes only? Won't it be approximately 2 amperes only, everyone? Very good. Now we know that the voltages have to be same across both. Voltages have to be same across both. So voltage across the shunt will be voltage across the galvanometer. Across the shunt, it is I into R, resistance, I do not know. Across the galvanometer, current 10 to the power minus 3, resistance 100. So from this, you will get Rs. This will become 10 to the power minus 1. This will become 1 by 2. So this will become 1 by 20, which is basically 0.05 ohms. So the shunt resistance is 0.05 ohms. If you use that small resistance, then you can measure currents up to 2 amperes. Are you able to understand it? How to solve this kind of questions of ammeter? Don't remember formulas. That's why I did not block anything. Many teachers make students by heart formulas. I pity such students and I wonder why those teachers make them by heart such formulas. You don't have to, you just have to remember voltage is IR and it is the same, it's a parallel circuit. That's all. And most of the times you will see that this approximation will help for solving the problems. Cool? Yep, very good. Now the next application, like I said over here, is as a voltmeter. I want to measure it as a voltmeter. So how do I make use of it as a voltmeter? What you do, a voltmeter is nothing but voltmeter, symbol for that either this or this. A voltmeter is usually connected in parallel across a device. In parallel across any device, let's say so this is my device across which I want to measure the voltage difference. Because it is connected in parallel across the device which you want to measure the voltage. It also means one more thing, guys. What? You cannot have you cannot have a small resistance, because if the resistance is small, all the current will go here, the device will stop working. Imagine you want to measure the voltage across a fan. If you connect the voltmeter, imagine the fan only stops working or it starts rotating slowly, then you are not doing a true experiment. It should be as it is. It's like I want to measure the pulse rate of a human being or the BP of a person. Imagine I put some device to measure the BP and the person only stops working. Imagine he's shivering. Then it is not a correct measurement. It should not affect the device. It should not affect the measured value. Getting my point? Like measuring the blood of a person. You cannot draw 1 liter of blood or some 7 liters of blood from a person and say, okay, let me test the blood. What are you testing the blood for? Got my point? So that's why you cannot draw too much of current. The device has to stay unaffected, which means the voltmeter has a very high resistance, and draws a small current only. It draws a small current only. It also means that an ideal voltmeter has infinite ohms of resistance. An ideal voltmeter has infinite ohms of resistance. Yes, correct. So, coming back to the point, how do I make a very large resistance from a galvanometer? No issues. You just take the galvanometer. It has Rg resistance. You add to it one more resistor, but this time this resistor is in series, not shunt, it is series. If you add both of them together, that's it, and you package it very nicely. Oops. That is exactly what a voltmeter is. So voltmeter is not too different from a galvanometer. Just you connect a resistor in series, that's it. If galvanometer is available for 500 rupees, you buy a 5 rupees resistor, 505 rupees, that's it. It becomes a voltmeter. You cannot charge 1000 rupees for it. That is now the two terminals, which is like the probes where you attach across the device to measure the voltage. So let's say the voltage that you want to measure is over here. This is the voltmeter reading. This voltmeter reading will be the net current multiplied by the net resistance. So whatever current goes through the galvanometer has to go through the series resistor. They are in series obviously. So the net current is just Ig. The net resistance though is nothing but resistance of the galvanometer plus the resistor of the series resistance. That's it. So this then becomes your voltage measured value. So this is how you can measure the voltage if I measure the galvanometer current. If I know the current, I can measure the voltage. This is the working principle of a voltmeter. Is this clear? Let's do a simple example so that you understand it. Again, I would repeat over here. Please don't by heart this equation. You know Ohm's law, just apply Ohm's law. Let me show this to you. Example. The full scale deflection current of a 100 ohm galvanometer is 1 milliampere. In order to convert it as a voltmeter of 10 volts, find the series resistance which will be needed. Find the series resistance which I will be needing. Let's try this out. Just draw a simple circuit. We know voltmeter is made of two resistors in series. This is galvanometer of 100 ohms. Remember, I can't pass more than 1 milliampere, which means 1 into 10 to the power minus 3 amperes of current. In series, you have one more resistor. I will call it RS. As a whole, it cannot measure more than 10 volts. That's the range of the voltmeter. That's it. This is our diagram for the voltmeter. So now I know voltage. Now I know voltage is nothing but your current multiplied by the resistance. V is IR. So what will be the current? Current is 10 to the power minus 3. What is the resistance? Both are in series. So 100 plus RS. 100 plus RS. This goes over here. This will become 10 raised to 4 is 100 plus RS. So RS will be 10 raised to 4 is basically 10,000 minus 100, which is 9,900, which is 9.9 kilo ohm. So the series resistance required is 9.9 kilo ohm. Then you have converted into a voltmeter of how many volts? 10 volts. Is this absolutely clear, everyone? This is how you convert it. So these are very beautiful examples to show how you can convert it into a voltmeter as well as previously ammeter. So if you know these examples, you will be able to solve this. So that was the end point of this particular chapter. Now I want everybody to comment down below because next chapter is very chintu mintu. It is magnetism and matter. We'll finish it off most likely in one lecture only. Okay. So get ready for the next chapter number 5 already. That chintu mintu chapter will be over. Then we'll move on to chapter 6. And slowly within no time, by November, I think we should be done with most of our NCERT. And you are prepared not only for NEET, 12th standard students are also prepared for your board exams. Got it? And by the way, there is a very big surprise coming from all of us for the students, especially of Karnataka as well as Maharashtra. So if you are a student of Karnataka or Maharashtra, maybe your friends, maybe your relatives, maybe somebody from your colony, tell them that something amazing is coming, because we were getting lot of requests, lot of students from Karnataka, Namma Karnataka and Maza Maharashtra. Prepare for CT exams, prepare for their state board exams, prepare for the COMEDK exams, prepare for MST CT, and there is nobody at a national level doing something for them. Don't worry, something really cool is coming. We already have the awesome Tamil and the Telugu channels for all of you who want to, learn in Tamil or learn in Telugu. We also have an English channel, but now something really amazing for Karnataka students and Maharashtra students. So stay tuned. Let them also know, because a big Dashara special is coming very soon. And very soon, yes, for Kerala too. I know a lot of students from Kerala are very interested, but we already have the English channel. So English is going to be the universal channel, like the channel which is holding all the channels together. But at the same time, we also need to cater to the needs as well as the studies of all the parents and students who want to learn and engage for their special states, their special state entrance examinations. Every state has a different need, and that is what we will be planning very soon. Thank you for all the love that you guys have been showering throughout India, and that is the reason why Vedantu always stands for our students. We'll always make sure that you get customized, personalized, channels, learning methods and innovative methods. At the same time, we'll make sure that you have all the national level channels as well. Thank you so much, guys. Take care. Do not forget to like and subscribe to the Vedantu NEET English. Take care. Bye bye. Hasta la vista.